Derivative feedback is usually combined with proportional feedback to give what's called a PD controller, proportional derivative controller. And that's a standard control scheme that's used in industry to control things like motors and furnaces. Again, a PD controller has the form that looks like this in block diagram, Kp plus SKD. And as we mentioned before, this is non-realizable. You can't have a derivative term here because you couldn't actually build that. Instead, there's usually a fast pole that's associated with this. For this example, I'm going to leave it in this form. In my example, the plant G of S has the form 1 over S squared plus S, and my desired system response is a natural frequency of 4 radians per second and a damping ratio of 2. If I look at first the poles of the open loop system has a pole at 0 and a pole at -1. The desired spec, omega n is equal to 4, zeta is equal to 0.2, corresponds to poles at approximately -0.8 plus or minus 3.9 I. If you need to verify that for yourself, you can just plug that into the standard form for a second order system and solve out for the poles of the equation. That means that the desired poles are somewhere here on the red dots where this is 3.9 and this is 0.8. There's some scaling issues going on here, but you can see the current system does not meet the desired specifications. So we need to add a controller on that. Once we add the controller, the system looks like this. We have the original plant. The output from the plant is X. We now create a new system where the input is no longer the input to the original plant. It's X desired. It's where we want the output to be. We compare the desired output to the measured output, multiply that by a gain, and take the derivative and multiply it by a gain. The sum of those go into the plant. We're interested in the transient response, so I need to know the closed loop characteristic equation for this. And by now you've done that enough that you should know that you can just write that down directly like this. This is the D polynomial, which comes from the denominator of the open loop plant. This is the N polynomial, which comes from the numerator of the open loop plant. And this is the gain, this right here. My goal as a designer is to find the values of Kp and Kd such that the new system satisfies the design criteria. When designing a PD controller, proportional derivative controller, I usually design for Kp first. If that satisfies the specification, I can stop and I don't need derivative control. Then I'm left with a simpler controller, easier to implement. If I can't meet the specifications with Kp alone, then I'll add in the derivative control. There are two methods for finding Kp and Kd in a PD controller. The first is a direct method, which involves matching coefficients. The second is to use an iterative method with root locus. To find Kp and Kd directly, we write down a desired closed loop characteristic equation based on the specifications, and then match the coefficients of the desired closed loop characteristic equations with the actual closed loop characteristic equation and solve for Kp and Kd. The key to this is you must know a valid closed loop characteristic equation. In a second order system, recall that given a PD controller, you can place the poles anywhere, which means that any second order characteristic equation is valid. If this was a third order plant, I would have to pick something, probably by looking at the root locus, finding something that's possible to do with Kp and Kd, and then solving for the coefficients directly. In this case, you can get a valid closed loop characteristic equation two ways. One is you can use the standard form, which is S squared plus 2 zeta omega n S plus omega n squared. Substitute in the desired values, 0.2 and 4. And so our desired closed loop characteristic equation is S squared plus 1.6 S plus 16 equals 0. Another way is to write down the closed loop characteristic equation directly knowing the poles of the system. We found the desired closed loop poles previously. They're right here. Now you can see directly it's been factored. S equals -8 minus 3.9i is one solution, and S is equal to -8 plus 3.9i is the other solution. So once you have a desired valid closed loop characteristic equation, you can then solve directly for the coefficients by matching. Again, my closed loop characteristic equation is s squared plus 1 plus kds plus kp. That comes directly from here. My desired closed loop characteristic equation is here. I match coefficients. These are the terms to match. Write down the resulting equations, and I have that 1.6 equals 1 plus kd, and 16 is equal to kp. Kp is equal to 16. Kd is equal to 0.6. Remember, this method only works if you know a valid closed loop characteristic equation. If you don't, then you need to use an iterative method with root locus, which is the next method. In the root locus method, I'm going to write down the closed loop characteristic equation in two forms, one where we can vary kp and one where we can vary kd. I've written them down here. Notice that these are the same two characteristic equations. I've just rearranged the terms. In the first one, the d polynomial is here, the n polynomial is here. In this case, d polynomial, n polynomial. My plan is to first vary kp and get as close as I can to the desired poles. Then I'll substitute the value of kp into this equation. I'll now have a new d polynomial, and I'll vary kd in order to find the solution. Let's look at some numbers. First, we're going to vary kp holding kd constant. That's this equation. So when kd is constant, set equal to 0, the root locus starts at the poles of the system, which are 0 and minus 1, and it goes to the zeros of the system. This system has no real zeros, so the zeros must be at infinity, and we know from root locus that the zeros will be at plus or minus infinity. And from the pattern I've seen before, it'll look like this, where they split at minus 0.5, halfway in between the two poles. Now recall that the desired location is here at minus 0.8 plus or minus 3.9 I. So I can get close, but I can't quite get there. The next step is to pick a set of poles that lie somewhere along the root locus that comes from varying kp, hold kp constant, and then vary kd. So I'm going to pick values of kp that are right here. I'm not going to find those values yet. I'm just going to do the design, and I'll come back and find the values later. But this is what I've done again. I've started with holding kd constant, done the root locus for kp. That gives me the blue line. Now I'm going to pick somewhere along that blue line and redo the root locus, and the place I'm going to pick are those poles right there. I'm now going to do a new root locus by varying kd. I'm going to draw on top of the old one so you can see what happens. My new set of equations are now here. This is for varying kd. So first, the root locus starts at the poles of the system, or the roots of the d polynomial. I need to find the roots of the d polynomial. So I take a value of kp, it's not 0, some value of kp, and I put it in here. And the value of kp that I pick is the value of kp that puts me at the green x. That's a valid location because it's on the root locus, so I know I can get there. So whatever kp is, I've picked that, so I'm right there. And it goes to the zeros of the system. Well, this has 1 0 at 0, but I need 2 zeros, so the other one must be out here. So now I'm doing the root locus for pole, pole, 0, 0. And that root locus looks like this. Now, I don't know exactly what this arc is or where the thing crosses over. So this may not be to scale, but this tells me what happens is I vary kp and then vary kd. If I vary kp, the roots come together and then go up. I can pick anywhere along that. If I pick somewhere along this line to hold kp constant and vary kd, what happens is the roots will come in, eventually meet up together on the real axis and split apart. Well, you can see that if I picked the value of kp high enough so that the arc passed right through the red dot, then I would have a value of kp and the corresponding value of kd. Now that there's a plan for the design, the last step is to go ahead and calculate values for kp and kd. You can do this iteratively, or you could go right to MATLAB and use the SISO design tool. First, let's set kd equals to 0, vary kp, and a couple of variations here. 16 minus 0.5 plus or minus 3.9 I. So I'm going to go with 16 for kp, cheating because I already knew the answer from before. Now the system looks like this, where kp is 16. I know that those roots put me here. And now I vary KD, and that'll take me along the green line. I don't need to vary it very much. I'm just going to start trying small values of KD and a little trial and error here, and I can end up with KD is equal to 0.6.